Let's get started. So today we are going to talk about multiple linear regression and the regression diagnostics. So here we consider more than one predictor in our regression model, and we would like to learn how to interpret it and then how to model um, this multiple when we have multiple predictors, and how to test the significance of the regression coefficients. And after building model, that's not the end. So you need to check your model carefully, so that whether you can find the on extreme points, and also check whether your model satisfies the regression modeling assumptions. So the multiple regression or multiple linear regression will look at the association between one dependent variable, which is the response y, and the multiple independent variables, which is the multiple predictors or the regressors. So the basic model is we assume the linear regression model, which models the relations between the one dependent variable y with the p vector of regressors of xi. So the p vector of regressors xi means that we have a p covariates or p independent variables, and we are looking at the association between y and p independent variables. The model has the linear it is a linear combination of the regression coefficients with the predictors, and we have error terms. And for this one, you can simply express as y xi transpose beta, which is xi transpose beta is inner product between the vectors xi and beta. So this beta is beta 1 to beta p. Xi is the xi1 to xip plus epsilon I. So that's the yi. And in general, you can use the linear regression model as the matrix form. So we have y, which is the vector, n times 1 vectors, and the axis is the n times p matrix. So we have n observations and p covariates, and then beta is the p times 1 vectors, and epsilon is n times 1 vector. And then so the yi is a response variable or dependent variable for ith statistical unit. Xi's are explanatory variables, and then it's called the covariates input variables, predictor variables, or independent variables, or regressors for ith statistical unit. And the matrix X is called the design matrix, and then we use this one, as a constant in the one of the predictors. And then the corresponding elements of the beta is called intercept. And beta is a p-dimensional parameter vector. Its elements are also called effects or regression coefficients. And we focus on the inference and estimation on the beta. And the epsilon is the error term. And the error term is assumed to be independent with the predictors. And this error term is the unsystematic part of this model, which is the part that is not explained by the axis. So here we have the regression model assumptions. So the the relationship between the predictor and outcome is linear. So we have linear relations between y and xi's. So we have the betas and xi's, they are linear combination, and the plus error term is equal to yi. So each term of beta is linearly related with respect to yi, and normality is the error term is normally distributed. And then the homogeneity of variance is that, so the variance of error terms is constant. So which means that the error variance is the same for all epsilon i's. And independence, the errors associated with one observation is statistically independent with the errors of any other observation. So the error for one observation does not affect the error for the another observation. And then our model is true. So which means that our model is is including all the proper variables. So this model is the true model. So so that's the one of the important assumption. So here, so these are the basic assumptions for multiple linear regression. And there are some problems or issues that we have to focus on. They are not the assumptions of the regression, but it may be a concern to regression analysis. So the first one is influence. So individual observation so can change your regression coefficients. So if you omit or add the observation, and if that changes your regression coefficient significantly, and it's the substantial amount, then we just say that observation is called influential point. And the collinearity is the other thing that we have to look at it, which means that the predictors are highly collinear. I mean, it means that they are linearly related. So it means that for example, you have two independent variables, x1 and x2, and then say your x1 is the approximately 2 times x2, then we say they are they have collinearity. Then this collinearity causes the problems in the estimating regression coefficients. So with these problems and assumptions, we have to look at after we fit the model. So then, what is the interpretation of the regression coefficients? So when you fit the linear regression model, you identify the relations between a single predictor variable x and response y under the condition that all other predictor variables in the model are held fixed, which means that you interpret the regression coefficient for single predictor variable, and then and then you make interpretation under the condition that the all other predictor variables as fixed as constant. I mean just a fixed. So interpretation of beta j is that is the expected change, or change change of the mean of the y, one unit change in x when the other covariants are held fixed. And then that is called the unique effect of xi on y. And then there's another term called the marginal effect of x on y. That's the correlation coefficient, or the regression coefficient on simple linear regression model relating xi to y. So this marginal effect is the relation between xi and y when there are no other independent variables. But this unique effect of xi and y is the linear regression coefficient for xi under condition that other covariants exist, and then we fix them. So there's some remark on here. So it is possible that unique effect can be nearly zero even when marginal effect is large. In that's the case, you have many significant variable which explains the variability of y, and then that captures the variability, the other variable, independent variables captures the variability of y in the linear regression, so that there is no contribution of xi into the variation in y. So if you just fit this marginal, just a simple linear regression on xi and y, the effect is large, which means the xi is important variable. But if you have other variables, and then if they are important so that their contribution is large for variation of y, and then if with the existence of the those other variables, the contribution of xi is small, so that the unique effect of xi would be the small. But the important thing is that the converse is maybe true. So unique effect of xi can be large while its marginal effect is nearly zero, which means that the contribution that other variables are making and the contribution of this marginal, if the xi is making, they are independent of each other. So using other variables, reduce the variability of yi that is unrelated to xi, and then you have, and then when you put the xi on here, it explains the necessary it explains the important part of the variation of yi, or it explains the apparent relationships with the xi and yi when you put the xi, so that the unique effect can be large. So marginal effect can be very small, but unique effect can be large, and also vice versa can be also possible. So to estimate the coefficient, regression coefficient beta, we use the ordinary least squares, which is the minimizing the sum of squared residuals. And then there's a closed form for the beta hat. So by using matrix form, this is x transpose x inverse x transpose y. And then this estimate is unbiased and consistent if the error have finite variance and they are uncorrelated with the predictors. So I will explain about the model fitting and the model criticism in the next video.